The actual formula we care about in chemistry is called a molecular formula. This is what the chemical actually is in real life. We just learned about empirical formulas prior to this video, and we're going to use empirical formulas as our stepping stone to figuring out what the actual formula is for the molecular formula. So by the end of this video, you should be able to solve for molecular formulas, the thing we actually care about as chemists. So as I just stated, a molecular formula is the actual number of atoms present in a molecule of a compound, hence molecular formula. If you check out this table that I've included here on this slide, we can see that the empirical formula, which we've talked about before, is the most reduced form of a formula for a chemical. However, when we compare that to the molecular formula in this column, we see that that's the actual number of atoms present for a specific compound of interest that we're talking about. So for example, if we look across that first row for benzene, we can see that its molecular formula is C6H6, but its empirical formula is CH. So CH doesn't tell us what the actual number of atoms are present for the chemical benzene. So what actually gives us the real information is the molecular formula, where it says, hey, benzene has 6 carbon atoms and 6 hydrogen atoms. Therefore, the molecular compound is the actual formula of the compound. And that's the reason why we care about it so much as chemists, because CH is not the actual chemical that we're interested in. In other words, the molecular formula is the not reduced version, whereas the empirical formula is the reduced version. So then why did we even learn the empirical formula to begin with? What was the point? We use the empirical formula as a stepping stone. It's a middle ground. We have to use it to get from percent to empirical to the molecular. So we need it in order to figure out the molecular formula of a compound, which is what we actually care about. Especially if you're like a CSI agent and you need to figure out what chemical was at the crime scene. You're just going to use the empirical to get to the molecular formula. As a side note and reminder from the previous lesson, notice I've drawn in these arrows right here. Those arrows are to signify the ionic compounds in this list: sodium carbonate and ferric oxide. Both of those are ionic compounds because you have a metal paired with a nonmetal in the compound. Notice that their molecular formulas and their empirical formulas are the exact same. Nothing is reduced. This is to remind you that anything that's ionic is already in its empirical formula. Therefore, it's already also in its molecular formula. So given the difference between a molecular and empirical formula, I'd like you to pause the video here and think about why it's more important to have the molecular formula than it is to have the empirical formula in real life scenarios. Go ahead and pause and think about it now. So now that you've had a chance to think about it yourself, here's an example I can provide you as to why a molecular formula is so much more important than an empirical formula. If we think about the two different formulas for formaldehyde, that's CH2O, versus the formula for glucose, sugar, C6H12O6, let's look at those two compounds' formulas and compare what they are to each other. If we were to look at glucose formula and reduce that down to its empirical formula, we would just find a common divisor. In this case, that would be 6. So we would divide all of these subscripts by 6. That would give us C. 12 divided by 6 is 2, so H2. And 6 divided by 6 is 1, so just O. CH2O. Well, that looks an awful lot like formaldehyde. The difference between glucose and formaldehyde is vast. One, you can mix glucose in your coffee or your baked goods and it tastes great. Formaldehyde is used to preserve like dead things. And formaldehyde is CH2O. So glucose and formaldehyde, in terms of the chemical structures, what they look like, are entirely different. Completely 100% different. And used for completely different things as well. So the real life application here is that formaldehyde is literally the empirical formula of glucose. But if we were interested in glucose as a molecule and all we had was the empirical formula, formaldehyde, that's not the same thing as glucose. So here it's very important to know glucose's molecular formula over its empirical, unless you want to put like dead preservative in your coffee and baked goods, that is. Those chemicals are entirely different from one another. So here are the steps you should know in order to calculate the molecular formula then, since that is the more important formula. Step 1 is to calculate the molar mass of the given empirical compound's formula. So in this type of question, you will be given the empirical compound's formula. You just have to calculate the molar mass of said empirical compound's formula, which would be given to you. Step 2 is to take the molecular mass, which would be given to you, that's the actual molecular formula's mass, again given to you, and divide that by the empirical molar mass that you just calculated from step 1. And the final step, step 3, is that after you've divided the molecular mass by the empirical molar mass you calculated, you will get a whole number. And if you happen to not get a whole number, you did something wrong. However, if you did it right, you should get a whole number. And once you have this whole number, you'll multiply all the subscripts in the empirical formula that was given to you by this whole number you calculated. And that will give you the molecular formula. These kind of questions are difficult to understand without seeing an example, so let's jump right into an example here. Notice that the question is giving me molecular mass. The molecular mass of a compound is 180.18 grams per mole. So that's one of my givens. And the empirical formula is CH2O, another given. Now they're asking me what is the molecular formula. In other words, what is the actual formula of CH2O? So first I would calculate the molar mass of CH2O. We know that each carbon brings to the table 12.011 grams per mole. Where did I get that number? The periodic table. Make sure you've got your periodic table and look at those little values underneath each atom. H brings 1.008 grams per mole per H, and there happens to be 2 of them. So we're going to multiply that by 2. And oxygen always brings 16 grams per mole per atom. So we're going to add together those values to find the molar mass of CH2O as our step 1. Grab your calculator to plug and chug. And our molar mass ends up being 30.027 grams per mole for CH2O as our empirical given formula. And there is that same calculation tidied up and rounded up. Instead of the 0.027, I just rounded it to 0.03. And for step 2, we now say divide the given molecular mass by the empirical mass. We were given our molecular mass again of 180.18 grams per mole. Divide that by the mass we just calculated, our empirical mass, which is right here. Notice that that's from the empirical formula, so that is the empirical mass. So taking 180.18 divided by 30.03, I get exactly the whole number of 6. Now moving on to step 3, I just need to take my empirical formula and multiply all the subscripts by 6. So back up to my original question. My empirical formula was CH2O, so C1 technically, H2O1 technically. Remember that there's always those invisible ones there. They're implied that they're there even though they're not shown. And now I'm going to take this 6 and multiply it by each of these subscripts down below. 6 times 1 just gives me 6, so that would be C6. 6 times 2 gives me 12, so that would be H12. 6 times 1 again gives me 6, so that would be O6. So we have C6H12O6. Hey! That's our glucose molecule from the previous slide. Notice that the CH2O was formaldehyde, and now we actually figured out that, hey, the actual molecular formula is indeed glucose, sugar. So if we were to have gotten CH2O from percentages that were found at a crime scene, and then a scientific machine in our CSI lab told us that the actual molecular mass was 180.18, we could then determine that, hey, that molecule found at the crime scene was actually glucose. So, the baker did it. All right, super sleuths, all of you CSI agents out there, go ahead and pause the video to give this one a try. Alrighty then, a well-known reagent in analytical chemistry, dimethylglyoxime, has an empirical formula of C2H4NO. That's our given, the empirical formula. And if it has a molar mass of 116.1 grams per mole, another given, what is its actual molecular formula for the compound? First, we need to calculate the molar mass of C2H4NO using our periodic table. So let's list out our atoms that are present in that molecule. We have carbon, we have hydrogen, we have nitrogen, and we have oxygen. Each carbon brings to the table 12.011, and we have 2 of those. So 12.011 times 2. For hydrogen, we have 4 of those, and each hydrogen atom has 1.008 mass. And again, there are 4 of them. Each nitrogen atom brings to the table 14.007 mass, and there's only 1 of those, so we could just multiply it by 1 or leave it as is, because anything multiplied by 1 is itself. And then we have 1 oxygen atom. That always brings to the table 16, or 15.999, but we're just going to round it, times 1. Grab your calculator and plug and chug all those values together. Now that we have all the multiplication done, we need to add all 4 values together to find the molar mass of C2H4NO. And our molar mass ends up being 58.061 grams per mole. All right, step 1 is complete. Now we need to divide the given molecular mass, which is the 116.1 grams per mole, by the empirical mass. So we're going to take this value here, 116.1, and divide it by 58.061. And we should get a whole number, remember, if we did this right. I end up getting 1.99999, so that is technically 2. That's a whole number, close enough, we did it right. So all we have to do now is take that 2, that's our multiplier, and multiply it by all the subscripts in C2H4NO. So we're just going to take that 2 and multiply that by 2, multiply the 4 by 2, the 1 by 2, and the other 1 by 2. What we end up with then is C4H8N2O2. And that would be the actual molecular formula of dimethylglyoxime, the compound of interest, right there. Now, I had mentioned that we needed to use the empirical formula to get to this point. Yes, so let's actually start from ground zero and work our way all the way through to the molecular formula, just like a CSI agent would. So if we say, hey, ammonia reacts with phosphoric acid, so there's an actual chemical reaction going on here, to form a compound that contains 28.2% nitrogen, 8.1% hydrogen, 20.8% phosphorus, and 42.9% oxygen. We need to first figure out the empirical formula, then we can use that to figure out the molecular formula. Let's give it a go. So we need to use our percent comp to empirical formula rules and steps, and the first thing we're going to do is take all these percent signs and just put a G there instead for grams. We're assuming that the entire compound is going to total to 100%, so we can do this with confidence and just remove that percent out of our lives and assume that it's grams of each atom type. We're then going to have to draw a magical line to freedom for each of these atom types to figure out the moles of that atom within the compound. Let's draw our magical line to freedom for each of these atoms present. We have nitrogen first at 28.2 grams. We have hydrogen next at 8.1 grams. And for phosphorus, we have 20.8 grams. And oxygen has 42.9 grams. Now all we gotta do is use our molar mass to get from grams to moles of each atom type present. Where do I get that molar mass? The periodic table, of course. If I look over at my periodic table, I can see that nitrogen has a mass of 14.007 grams per mole for each nitrogen atom. So I'm going to put 14.007 grams per 1 mole of nitrogen. I put the grams on the bottom so that my grams can cancel top and bottom, and I am in fact left with moles. Let's do that for the rest of these atoms before we calculate. Hydrogen has a mass of 1.008 grams per 1 mole. Oxygen has a mass of 16 grams per 1 mole. And phosphorus has a mass of 30.974 grams per mole. All right, let's go through and just divide all of these out. So for nitrogen, 28.2 divided by 14.007, hydrogen, 8.1 divided by 1.008, phosphorus, 20.8 divided by 30.974, and oxygen, 49.2 divided by 16. All right, the next step for my percent composition to empirical formula is to divide all of these mole values by the smallest mole value we've calculated. Out of these values, the 0.6715 is the smallest, so we're going to divide all of those answers by 0.6715. All right, now that we've divided all those out, we see that we're all pretty close to rounding up those values, so why don't we do so? 2.99 is just going to get rounded up to 3. 11.9 is going to be rounded up to 12. Phosphorus was just 1 because 0.6715 divided by itself is just 1. And 3.99 we're going to round up to 4. So what we currently have now is an empirical formula of N3H12P1O4. So that would look like this. Currently, that's our empirical formula. Now we can take that and figure out what the molecular formula should be. So we chucked that chemical into some scientific machine in our lab, and it told us that the chemical's molar mass was 149 grams per mole. So using that, we can now calculate the molecular formula by first figuring out what the molecular mass is of the empirical formula that we just calculated. We have 3 N's, and each N brings to the table 14.007 grams. So for nitrogen, we have 14.007 times 3. For hydrogen, each brings 1.008 grams to the table, and we have 12 of those. For phosphorus, we have 1 phosphorus, and each phosphorus brings to the table 30.974 grams, and there's only 1 of those. And each oxygen brings to the table 16 grams, and there's 4 of those. So let's figure out what the empirical molecular mass is. We got to add up all those values together, and we get a value of 149.091 grams per mole for our empirical mass. Now to calculate the molecular formula, we were given the molecular mass of 149. Hey, isn't that the same thing? Okay, well, let's see. Step 3 was to divide our molecular mass by our empirical mass. If we divide those two things together, we get 1. And then we would just multiply that 1 by all the subscripts provided, which still gives us the same answer, N3H12P1O4. So in this case, our empirical formula and the molecular formula are the same thing. So the chemical that we yield when we would mix ammonia and phosphoric acid together is N3H12PO4. Think you got it? Go ahead and give this one a try all on your own. Pause the video now. Want to see if you did this one correct? Let's start from the top. We see that the molecular mass of a compound, the given, is 92 grams per mole. And the analysis in a lab told us that it contained 0.606 grams of nitrogen and 1.39 grams of oxygen. Let's figure out both the empirical and molecular formula. Now in this case, we were already given the data in grams, so we didn't have to just replace our percent sign with grams. But we're going to start the same way we always do anyhow. We're going to take our nitrogen and our oxygen and draw a little dimensional analysis, magical line to freedom for both, because we're going to first find the moles of each. Our givens are 0.606 grams of nitrogen and 1.39 grams of oxygen. To get from grams to moles, we always use molar mass, which is found on the periodic table. So for nitrogen, we have 14.007 grams in 1 mole of nitrogen. And for oxygen, we have 16 grams per 1 mole of oxygen. We just got to divide those values in our calculator to figure out the moles of each. Between those two values, we need to pick the smaller one to divide both by. The smaller one is 0.0432 for nitrogen, so let's divide both of those mole values by 0.0432. Excellent. So we have 1 N atom and 2 O atoms. So our empirical formula looks like this, NO2. Now let's figure out the molecular formula. It could still be NO2, but we have to double check given our mass of the actual molecule. Our molecular formula is 92 grams per mole. First, let's figure out what the empirical formula's mass is. We have 1 N, that's 14.007, plus 2 oxygens. Each oxygen brings 16, so times 2. When we plug that into our calculator, we end up with an overall empirical molecular formula mass of 46.007 grams per mole. Our next step is to take our molecular mass, our given, and divide it by the mass we just calculated for our empirical formula. So 92 divided by 46.007 should give us a whole number, And that whole number happens to be 1.999, close enough to 2. So we'll just say 2 is our whole number. 2 is our multiplier for our empirical formula. We're going to take our 2 and multiply it by the subscripts that are present in our empirical formula. So our actual molecular formula is N2, because 2 times 1 gives me 2, N2, and 2 times 2 for oxygen gives me 4, so N2O4 is our actual molecular formula for the compound of interest. Overall, in summary then, the percent composition is the percent or the grams of each atom type or element that is present within a compound. The empirical formula is the reduced and simplified formula that we use as a stepping stone to get to the molecular formula, which is the actual molecules formula, the thing that's not simplified, the thing that we care about truly as chemists. What is the actual formula? In order to make sure that you understand the differences between these two types of formulas, empirical and molecular, I highly recommend that you draw one of these little brain map charts to organize the differences and similarities. So for example, the difference for a molecular formula versus an empirical formula for one of these bubbles is that the molecular formula is the actual molecules formula, while the empirical formula is the reduced form of it. A similarity, however, is that they're both formulas that both contain a certain number of atoms. Go ahead and try filling out the rest of these bubbles to make sure that you understand the differences and similarities between empirical and molecular formulas. And of course, if you really feel like you're understanding this material, and you might be developing a bit of a headache from learning all these different steps, why don't you try and figure out the empirical and molecular formula for ibuprofen? And I truly apologize if now you need to go take an ibuprofen after you've learned this lesson. If you'd like to check your answer and make sure you got it right, please say so in the comments below and I'll be happy to let you know. Please give me a quacks up and subscribe to my channel for more educational content and to help others like yourself find this video and help them too. I hope your day is just ducky.
No ducks, no glory.